So welcome back to Physics of Music. And what we're going to talk about today is more about oscillations in physical systems and how to understand why those arise from the various forces that are present and how to understand the properties of these oscillations. And the reason that we're doing this is because oscillations are very important when it comes to understanding the behavior of musical instruments, understanding what is sound, and understanding how sound travels and affects our ears and ultimately allow us to hear the music. So let's talk about what we did last time. So we had the idea that if you have a system in equilibrium, so basically an object which is just sitting there not moving, then there aren't any net forces on that object, but usually you have some forces that are just canceling each other out. If you have an object on a table, there's gravity, but then there's an upward force from the table and the forces cancel, so you don't get any rate of change of velocity, and it just stays there. A nice example is the one that we just saw, and that's a mass on a spring. And there again, you have the gravitational force pulling down on the mass. And if the mass is in equilibrium, then the force on the spring that you get from stretching it exactly balances that. And so the net force is zero. But in many situations, most situations when you have something in an equilibrium configuration, if you then perturb that away from the equilibrium configuration, so in the spring case, if I move the mass downward a little bit or upward a little bit, well, then those forces that were balancing before usually no longer balance. And what we typically have is the idea of a restoring force. What you find is that if you displace something in one direction away from equilibrium, then typically the force acts in the other direction. So you can think of that as being the reason why it was fixed there in the first place, that if you try to move it away in one direction, that there's some force that moves it back. And so we understood in the spring example, if you pull the mass down a little bit, then the force of the spring is now greater than before in the upwards direction. Force of gravity stays the same, and so there's an upward force. If you pull it up a little bit, now the spring force is less, and so the gravity force dominates and the net force is down. And so this is in general the idea of a restoring force, any force which is in the opposite direction compared with the displacement from the equilibrium position. And when we have forces like that, then we end up getting oscillations. Okay, so before we understand that, I just want to point out that even though this mass on a spring system is kind of artificial, the same thing happens in various situations that we'll be interested in when talking about music. So for example, if you have a guitar string and you displace it one way, then there are forces that are leading it to come back to the straight equilibrium position. If you displace it the other way, then there's forces bringing it back. Similarly, if you have a drum and you hit the drum, then temporarily the drum head is displaced away from the flat position that it wants to be in. And what will happen is that then the forces will try to bring it back. And then it might go past, and then there'll be forces trying to bring it back down again. And so these restoring forces show up in all sorts of systems, and especially the ones that we're going to be talking about when we talk about musical instruments. Okay, so we've seen in an example with this mass on the spring that it oscillates up and down. And let's try to just understand that a little bit more precisely in terms of our rules of physics, in terms of the rules that we had for predicting how positions will change and how velocities will change. Okay, so I want you to actually think about this question for a minute, maybe pause your video. This is just a picture of 5 different positions of the mass on the spring at various different heights, going from the lowest height to the highest height. And what I want you to do is just basically for each picture, especially for the second and the fourth picture, ask yourself, what is the object's velocity? Is it 0? Is it upwards? Is it downwards? And also ask yourself, what is the direction of the force? And then is the object speeding up or is it slowing down? So pause the video and maybe think through that for these various situations, and then we'll talk about it. Okay, so let's have a look at what's going on in the 5 different pictures. So in the first picture, we're at the lowest position. Maybe this is when I just pulled the mass down to the lowest height. The velocity there is 0. But because we've stretched the string downward, the spring downward, then the force goes upward. And so that means that even though the velocity is 0 now, it's going to start moving upward because the rate of change of velocity is in that positive upward direction. And so in a little while later, you'll have an upward velocity. This is question 2. And the force, it's still upward because we're still below the equilibrium position. And so what that means is that the velocity is going to keep increasing. So this thing is going to be accelerating upward. And by the time it reaches the equilibrium height, it'll be going faster than it was in picture number 2. At that equilibrium height, now the forces are 0. That was the definition of equilibrium height, when that was the place where all the forces cancel to each other. But that doesn't mean that the object is going to stop at that height. What you notice is that at that point, you still have a velocity which has been built up from all the forces so far. And so rather than just sitting there, it's going to continue moving upward. And so as soon as it gets above the equilibrium height, now the forces are restoring forces that act downward. And so those forces then tend to slow down the object. And when you eventually stop, that's when you get to your highest position. It doesn't stay there forever because there's now still downward forces. In fact, that's the place where the downward forces end up being largest. Okay. And so this is how we can understand the motion upward, accelerating through the equilibrium height and then slowing down and then getting to the highest position. And then from there, it's just the opposite. Now the downward force is going to cause an increase in downward velocity, and that will continue to increase until we get to the equilibrium position, and then it'll start slowing down, and then eventually we get back to the situation where the velocity is 0, and then we're right back at the start, and so then it repeats. Okay, so we've seen how the restoring forces acting in this system, if I have some initial displacement away from the equilibrium position, either below it or above it, will lead to an up and down motion that will just repeat and repeat. So it's a periodic motion. Okay, and that's what we see in the demo. I'm not sure if you can still see that over here. Let's see that. It's still going. Okay, so I want to start talking about the properties of that periodic up and down motion. And to get you started, I want you to think about what would a time graph of that motion look like. So take a minute, pause the video, and sketch a graph of the height of the mass versus time over several oscillations, assuming that we start by pulling the mass to the bottom point. Okay, well, this is what I came up with. It's not a very nice looking graph. Probably yours was better. But basically what I knew was that it started at the bottom and that it was going to go up at a later time to some higher position and then come back down and then go back up and then come back down. And it repeats. And the time between the repeats is the period of our oscillation. So one thing you notice is that I drew this kind of smooth. It could have been like a sharp zigzag, but I drew it a little bit smoother. I probably could have drawn it even smoother. And you might ask, well, how did I know that? Why should it not be just an up and down zigzag? And so that actually has to do with something that we saw in the previous slides. Remember that as it moved upward, originally it started going up with some velocity, and then it was faster, and then it was slower again, and then it stopped. And so basically the speed here, that's how quickly the height is changing with time. It's basically going to be how steep is this part of the graph. And so where it's steepest in the middle, that's where it's going up quickest. And then as it gets higher, then it should slow down and then stop. Okay, so probably my line is actually, this is probably too much like a zigzag. Probably it should go up, and then it should kind of gradually curve down, and then gradually get steeper again in the downward direction. Okay, we're going to see the real graph very shortly. So, but you might ask, like, what determines that shape? And in general, it's going to be different depending on the nature of the object that I use, the spring that I use, or wherever the restoring forces come from. So I could do this with a spring. I could do it with, I don't know, one of those stretchy exercise bands. I could do it. I could hang a little weight from a marshmallow and watch it oscillate up and down. And so depending on exactly what I use, the details of these restoring forces are going to be different, and I'm going to end up getting a different shape. Okay, so you might well have this shape that I've drawn for a certain kind of object, a certain kind of stretchy thing, and a different shape for something else. But what I want to do now is talk about a very special situation that is in some sense the most important example of restoring forces. And so what we're going to do is talk about a specific example of how the forces might behave as a function of like how much you stretch it, how much you've displaced your object from the equilibrium position. Okay, so there's a certain relation that shows up in a lot of systems. And in fact, it shows up in almost any system that you perturb from equilibrium, as long as you just perturb it a little bit. Okay, so it could be that spring back there. It could be a stretchy exercise band. It could be a marshmallow that you've got something hanging from. As long as you don't try to stretch it very much, if you just move it a little bit, then you end up finding this universal rule, which is known as Hooke's law. So the rule is that the force is proportional to how much you stretch it or how much you displace the object. Let's have a look at this equation and understand where does that show up in the equation. So the equation says that the force on our object, it is equal to some, K is just a constant, it's just some number. So that's going to depend on how stretchy or how stiff your spring is, for example. So think of that as just some number. The minus sign here is going to tell us that it's a restoring force, meaning that if I displace the object one way, then the force is in the other way. And then the important thing is that the x here, that's the distance from the equilibrium position. And so this means that the further I displace the object, the stronger the force is going to be. Okay, so mathematically we say that the force, or the strength of the force, or the magnitude of the force, is proportional to the displacement from equilibrium. And so that specifically means that if I double the displacement, I double the force. Okay, so it didn't have to be that simple, but that's what Hooke's law is telling us. Or if I take 4 times the displacement, it's going to be 4 times the force. Okay, so it's not just that the force gets stronger as I increase the distance, it gets stronger in this very particular way. And as I said before, that happens to be the actual way that these restoring forces get stronger, as long as you don't displace things very much. So for very, very many systems. For systems like the one that we have in the background there, if you can still see it, then, so that's a spring. One of the nice things about these spring systems is that Hooke's law actually applies pretty well even for displacements that are not really tiny. Okay, so that's one reason why we often talk about springs when we're talking about examples of this physics of oscillations. Okay, so what I want to do now is actually show you a simulation of what the oscillations would look like if we have Hooke's law. Okay, so what we'll do is just use the physics that we've understood in the previous lectures. So we'll use the fact that if I know the restoring forces obey Hooke's law, then I could make the precise predictions about how the positions and the velocities will change with time. Okay, so we're going to use the fact that the rate of change of position is the velocity, that's true at any time, and we'll use the fact that the rate of change of velocity is equal to the force over the mass, which in this case is equal to minus kx over the mass. Okay, and so as long as we know the position of our object and the velocity at any time, we can predict how those things will change with time. And so this is enough physics to know or to predict what's going to happen in the future as this object oscillates. Okay. So in the next video, we're going to start by seeing that simulation. I'll actually just put it into a computer and we'll see what it looks like. And then we'll start to understand the detailed quantitative properties of that motion.